Okay, so again, one more time with the centroid, and just to kind of talk about that, and I'm going to put a triangle up there one more time. A centroid goes to the midpoint. It actually goes to, like, if we cut these in half again, that looks like it's about halfway. So if I make that line go there, that looks like it's halfway. If I make that line go here, and that's about halfway. So I make that line go there. Oops, I missed, but you get the picture. Again, that's called a centroid. And yesterday I mentioned the whole median piece. A median is nothing more than something that cuts it in half. Okay, so it goes to the midpoint over here. All right, so these are the midpoints of those sides. But again, it goes to the middle or the median of the opposite side. Okay, so I think we talked about median yesterday, but just to make sure, that's kind of what it was doing. The next one that we have is called an altitude. And something that with me last week, I was obviously, you guys know I was gone last week and doing what I needed to do. I needed to fly, okay? And so when I was in the airplane, they fly at a comfortable altitude of how many ever 1,000 feet. What does an altitude mean? Anybody know? Like in a plane? How high are you going in the air? Right. So an altitude is how high you are up in the air. And that's like from the bottom of the plane directly straight down. And so when you make an altitude, the altitude is going to come from a vertice, so let's call that A, and it's going to come straight down and drop and make a 90-degree corner. Does it go to the middle always? No, but it could. If I go to the other one and make this a 90-degree corner, I'm trying my best. It's probably right in here. That's probably where the 90 degrees is. And again, same thing if I go here. That's probably 90 degrees there. We are not going to the middle of the other side. We are going to the opposite side and making a 90-degree corner. Okay? It's not a perpendicular bisector, because that would be something that cuts the side in half and makes the 90-degree corner. It goes from the opposite side and goes, or from the vertex to the opposite sides and makes a 90 degrees. These are known as altitudes. And in your notes packet, that's the next thing that we have. It says an altitude of a triangle is the perpendicular segment from a vertex to the opposite side or to a line that contains the opposite side. And here's what they mean by that part. Like this one here is an acute triangle, so all the altitudes intersect on the inside. Not necessarily true if we have other shapes. So building a little bit bigger triangle. First and foremost, what kind of triangle is this? Obtuse triangle. Okay. So if I make the altitudes, first of all, I have to come from this point here and go to this line over here and make a 90-degree corner. I think it's pretty much straight this way. I'm pretty good at that, like so. Okay? The problem becomes on these, I think, Riley, you were the one who said it was an obtuse triangle, right? An obtuse triangle is an angle that's bigger than 90 degrees. If I go from this point, let's call it B over here on the very far right, and try to go to the line that has CA, it's not going to be 90 degrees inside the triangle because of the fact that that's an obtuse angle, like you said. So what has to happen there sometimes is sometimes these lines need to be extended in order for me to make this drop straight down to make a 90-degree corner. So sometimes these altitudes go outside. Same thing with the one from C. Because we said it's an obtuse angle, which was 100% right, I can't make it 90 degrees unless I drop it straight down. Okay? Anybody in here, like in construction class? or have built anything? No? Okay, just asking. Because there's something that we have in construction items like, it's called a plumb bob. And basically what it is it's a string with a weight attached to it, where we attach it to the top of the wall and then let the thing hang so that we know how to make the walls straight. It's an easier way of doing it. Okay? So that's what it means to be in altitude, is when it comes straight down. Now, if I were to extend all those, they would hit at a certain spot, and that is called the orthocenter. So if I were to continue these on forever, they would come in here and meet at a spot as long as my lines were straight, which they're not, so I'm going to make this bigger. But this is called the orthocenter. So yesterday we talked about a centroid. That was when all the medians met. This is an altitude, so therefore it's called an orthocenter. This up here in the middle on that triangle would be also the orthocenter. And the theorem that we have for that, it says the lines containing the altitudes of a triangle are concurrent, which again means that you have 3 or more lines that hit. This point of concurrency is the orthocenter, and then it goes on to say in their diagram that lines containing AF, BD, and CE meet at the orthocenter G and ABC. And then in the pictures or in your notes packet, it says acute triangles, that orthocenter is inside of it, like the one I have up there in blue. If it's a right triangle, it's going to be on the triangle. And I didn't make a right triangle, I made an obtuse and an acute. And then an obtuse is going to be outside of it. And then on the bottom of that page that we have for section 6.3 in your notes packet, it gives you kind of a cheat sheet, if you will, as far as all the different ones that we've talked about. It gives you perpendicular bisector, gives you an example, and then it says the point of concurrency is the circumcenter, which we've been talking about the last couple days. Angle bisector gives you an example, and it calls it the incenter, which we talked about the last couple days. Then it says median, which was yesterday, and it talked about a centroid, which again was yesterday. And today, the altitudes meet at the orthocenter. Okay? So, on to your worksheet. Some of this stuff is going to be just like yesterday's. So, Ty, which one do you want me to do? 1, 2, or 3?
2.
Okay. It says JA is 72. So this line right here is 72 somethings. Okay? We want to find JQ and QA. So we are finding J to Q, and then we're finding Q to A. When you have the entire length, you need to use the fractions for this. Unfortunately, that's the only way that you can get around it. Do you want to find the red one or the black one that I colored in? And by the way, it doesn't matter. You get to choose. Red. And to be fair, I'm glad you picked that one because that is the easier one. All right? The red one, or the shorter one, you multiply it by 1/3, which, you guys, is the same as dividing it by 3. What's 72 divided by 3? How much?
24.
24. So Q to A was 24 somethings. So now I have this is 24. The whole thing is 72. How could you find the other piece?
Subtract 24 from 72.
Yeah, that's one way. You can subtract 72 and 24 to get the answer. Or, as I talked about it before, remember the short side is just half as big as the that medium side. So I could also just multiply it by 2 and you get the same answer. So to find JQ, you could take 72 minus 24, or you could take 24 times 2, or you could take 72 times 2/3. All of those will give you the same answer. Which one seems easier to you? Which one seems easier?
24 times
Okay. What's 24 times 2?
2, 48.
48. So on 1 through 3 on your worksheet, which Ty picked number 2, that is 100% just like yesterday's. Okay? So there's number 2. On 4 and 5, it says find the coordinates of the centroid. I'm going to do number 4. I'll pick that one. And this is also 100% like yesterday's. It's just another couple problems of it. So U is that 3, 3, 1, 2, 3, up 1, 2, 3, make a dot. There's U. V is at 3, 4, 5, down 1. This is V. And negative 2, up 1. This is W. So if I connect my dots, there I am. Now, remember, a centroid is going to the middle. From W, for instance, over to the middle of UV. This looks like it's the middle right here. If I connect those dots, there's the first median. From W to U. Looks like that's probably the middle, right about in here. Connect the dots. This is probably the middle right in here. Connect the dots. What order pair did they all hit at?
2, 1.
2, 1, looks like to me. Good job. So the order pair of 2, 1 is your answer for number 4. Does that make sense what we do for 4 and 5?
Yeah.
Centroid goes to the middle. Then 7 and 8 will say tell whether the orthocenter is inside, on, or outside the triangle. Then find the coordinates of the orthocenter. So now this is the new stuff. So Branson, because it's almost your birthday, pick a number 7 or 8.
8.
So first thing I'm going to do is I'm going to plot those ordered pairs. So 1, 2, 3, down 1, 2, make a dot. That's D. 1, 2, 1, 2. That's E. Oh, that's pretty close. And over 1, up 2, that's F. So if I connect the dots on this, I'm going to make my line smaller because that's really tight there. Okay? This is the kind of triangle it is. Branson, because I'm pretty sure you know. I have all the confidence in the world in you. What kind of triangle is that? Is that an acute, right, or obtuse triangle?
Obtuse.
I would think so too. That D to E to F, that looks pretty big, doesn't it?
Yeah.
Yeah. So the question's going to be, first of all, would the orthocenter be inside, on, or outside of the triangle? You said it's an obtuse triangle. I agree with you. So therefore, it's going to be outside. And that's on your notes packet, right there for you guys to see. It says the 3 different scenarios. If it's an obtuse triangle, it's outside. It says it right here on your notes packet. Now, to find it, I'm going to make altitudes, which I'm going to make in red. In order for me to go from F to DE, I have to go down out here. I can't go inside the triangle. It's not possible. Okay, so that's going to be outside of it. In order for me to go to E, it looks like I'm going to have to go this direction to make that 90-degree corner. And to go from here, it looks like I have to go somewhere in this category, this ballpark. And so when we start to come up with all these different ones, this is probably a little bit more in here, it's going to say, where do they all come together? What order pair is that? 1, 2, 3, 4, 5, 6. Looks like it was at the order pair of 1, -6. That's what you do for 7 and 8. And that happens to be number 8. Number 9, it's asking you a question. It says, to transport a triangular table, you remove the legs. You secure the glass top to the frame by looping a string from hole in each vertex around the opposite side, and then pulling it tight and tying it. At what point of concurrency do the 3 strings intersect? It's asking you, is it a circumcenter, in-center, centroid, or orthocenter? That's what it's asking you. And on 10 and 11, it's asking you to do more centroid stuff, which is the 1/3 and the 2/3 business. Okay? What do you guys think?